So it's recording. Okay. So first of all, I'm still grading our exam, and we'll be done tonight or tomorrow morning. Definitely before tomorrow afternoon. And I'll load the grades to the Canvas, but seeing them online because it's going to be on through the Speed Grader. I'll upload my grades there as well. And then about the homework, we'll finish the column design and column analysis and together tomorrow. And then we'll leave the homework tomorrow. You have a week to finish the column design. So let's turn them in. But for the last homework, which is for the bound and development lens, which we do not have time because the last day is next Friday, we're just gonna leave the homework to you guys to finish, and I will upload the solution so you guys can compare notes. Okay, so that's what we're gonna do about this homework and the exam. Now, new information about the final. I looked through the content we have covered so far. We're really good. We have covered most material. And for the exam, I don't think we're gonna do the cumulative fashion. Like I mentioned last time, we're probably gonna separate the exam in two parts. The first part will be short answers, conceptual problem. And those are gonna be covering the entire section, but heavily focused in the one-way slab and the column design. And we'll talk about the developer lens a little bit next week. For the rest of the exam is going to be a problem-solving exams. So we have 4 problems, 4 to 5, depends on the last problem still debating right now. And those problems will mainly cover the serviceability one-way slab, column design, and the bound development lens we're going to cover next week. So those is going to be the basic design for the exam. Now, as I was grading yesterday, there are several things I want to point out. Now, first of all, you guys done a good job, actually. The average grade I can expect to be higher, if not much higher than the first midterm. So congratulations, good job, all right? But I see some problems as well. I see some answers are quite similar. Some erroneous solutions are following some patterns. Now, I don't think there's any inappropriate behavior happened. Maybe some chit chat and converting messages. I really don't think that's helping you because I can see it. So since I haven't gotten any serious patterns that I feel like it's definitely inappropriate behavior, so I don't think there's any grading to be discounted yet. But I strongly encourage you not to do that in the final exam. And to consider that for the problem in the final exam, try to vary some numbers. I still want to see what kind of version exam you have. So this way we have less of this behavior or chance of this thing might happen. The day of final, by the syllabus, I believe it's 12th. And I intend to release the exam on the same day as noted by the register office, by the calendar. Like I said again, I would like to design maybe 4 versions or 5 versions, 6 versions of the exams with different numbers. And at the day it comes, I will email a group of you guys who will be working on specific version of the exam. So this will have less of a chance having overlapping numbers and solutions. Okay. All right, so that's what we have for the rest of the lecture and the final exam. It's been a challenging semester for all of us. And I really understand that we're fighting really hard to get this thing going. So appreciate your effort for joining this online, okay? So now let's continue our lecture, which is on the column design, okay? So quick recall, last time we mentioned several different columns, right? So let me go back to see this. So we mentioned that last time we are focusing on the short columns. And we have the short columns meaning compression, cylinder column, compression plus bending, and we have the buckling. Okay, now it may be a little bit misleading, but we do also have bending in the first category. But I would say I wouldn't say insignificant. I would say little mild bending, right? So just put it here, mild bending. Okay, that is, we do consider moment caused stress, but we do not consider the moment caused deflection in the short columns. Since we're not going to test you guys on the deflection of the columns, and we will not discuss the deflection caused by the bending moment on the column. Okay, so that's the least worry. So right now, let's take a look what kind of stress state we have on the column. Okay, so first of all, let's take a look at the columns and axial strength, right? Axial strength. Now we all know that column is good in compression. Column is good in compression. It's a very significant vertical members, right? So for a given column, subjected to axial compression, which is quite typical, axial compression, which is quite typical. And let me draw it so you can have a visual image. So say before I have a column just like this. Okay, so it's a side view. It's a side view, all right? And assuming I have a very short column, has a certain length of L, and I have reinforcement in it. Okay, I have a reinforcement in it. Bars, these are the bars. And by the way, this is side view, okay? This is side view. Okay, and now when I apply a compression force, okay, what really happens, I'm gonna use red, is that it will be compressed, right? The whole section will be compressed. The whole section will be compressed, okay? Now, assuming the whole column has been compressed by a strain epsilon, okay, and mass balance length, you get the total deformation delta, right? Now, we have to make a first assumption here is that we're gonna assume perfect bonding. So what does perfect bonding mean, right? So it means epsilon C in concrete, the strain in concrete equal to the strain in steel, Now that is slightly different from the bending from the beam that we talked about before, Okay. Now, taking a look at the section now, say if, switch the color, I look at the force versus deformation response or strain response for the concrete. Okay, I use PC, that is the concrete. Okay, that is a concrete. Then this is strain. Now I would have a nonlinear response. Nonlinear response is concrete is nonlinear. Concrete is nonlinear, right? And I know that I have a force for the concrete equal to the stress in the concrete multiplied by the area in the concrete. Okay, but the problem is it is nonlinear. Right? The response is nonlinear, so I cannot use one stress. I have to use an effective stress. We use that concept in the flexure theory. So I'm going to say the PC, right, the concrete stress, or the maximum force can take the pound by the concrete section PC max equal to a factor, let's just call it K3, F prime C AC. Okay. Now this looks a little bit similar from flexure, right? In the flexure, we have K3, the factor equals 0.85. AC is actually the compressive zone area. But in this case, AC is just the concrete, right? So AC is area of concrete in the column. Okay. So that is the force response of the column from the concrete part. All right. So coming back, let's take a look at what happens for the steel. All right. Now, as you know, the steel is elastic plastic behavior. What does it mean, right? It means that they go through an elastic region, which is linear line, and then yield into a plateau like that. And now, since I know that this is the PS, this is steel response, okay? Oh, this color is inconsistent. Let me try to change back. So this is the force from the steel. So now, if I say this is the max, okay? So this max force will equal to Fy, which is the yield strength of the steel, multiplied by the area of the steel. Right? So this is the area of steel. Now combine these two, you get the final response of the column. you get the final response of the column. Okay, so eventually what you get is the response from the steel plus the response from the concrete, and then you get something like this. Okay, so this is PC, this is PS, and this is the P. Okay, this is string. All right, and now let's call the maximum force that the column can sustain is P max or P0. Okay, P max equal to P0. Let's just define that. Okay, then we're seeing an equation like this. So first of all, P0 now, we have two components. The total compression of P0 now has two components equal to a K3 F prime C AC plus Fy AST. Okay, and now let's define some parameters. So K3, okay, was defined as 0.85. Now be careful here, it's determined by experiment. Okay, so we didn't do a whole lot of analysis to determine this factor K3. Basically, we just test a bunch of columns. When we say bunch, thousands of columns, and summarize the table and try to do regression analysis. It's kind of our old time machine learning for civil engineers. Actually, we discovered the machine learning back in the 70s for civil engineers, but that's another topic, right? And then back then, we used regression analysis to find out this factor to 0.85. Okay, and then define the concrete area AC equal to the gross cross-section area minus the area of steel. Minus area of steel. So now, with this, P0 equal to a 0.85 at prime C bracket inside AG minus AST, and then plus FY AST. Okay. So AG equal to gross area of section. AST defined as area of steel. Okay, so you can see that this is essentially the nominal load. The short column can carry. And it has both the concrete component and the steel component. Okay? So this is not bad at all. It's actually straightforward. Right? So for a short column that barely only compression, we can just go ahead and do this. Okay? So which is not too bad, but the problem is that most of the time, so however, bending often present most of the time. Why, right? Why? Right? So let's take a look, right? Let's take a look. What happens? All right, so let's open up, and the other thing is the compression or PM or compression. Let me use this would be better. So axial forces, bending moment, interaction diagram. Okay, the key word here is interaction diagram. Okay, you see that all the time. Okay, so what is interaction diagram? What does it look like? Right? So first of all, before we go there, let's do a basic stress analysis, right? So TM interaction occurs when force or axial force is applied with eccentricity. Okay, or when errors or defects fabrication defects are present in columns. Okay, now these two reasons is actually the same thing. Is actually the same thing. Why? For example, if I have a column, right? For example, I have a column. So scenario one, let's just say scenario one. I have a column. So it happened that my beam sitting on top of the column is not, this is the loading pad. This is my column. So my force, if this is the central axis, right? Central axis of the column, I'm gonna use my red. And my actual force is actually right here. So I will end up with an eccentricity, okay? Eccentricity when my force applied to the column, when my force applied to the column, okay? So that happens a lot in the reality, right? You will never be able to precisely place your beam on top of the column, okay? And then this is one scenario. The other scenario, right? What if when I fabricate my column, right? So my column is right here, the section wise. My reinforcement supposed to locate here. Right, so these are my 4 corner bars. But unfortunately, I'm gonna have a eccentricity of my reinforcement, messed up the whole thing. So I cause the shift of the centroid, right? So when my force applied, right, suppose in the middle of it, and then I end up applying with eccentricity E here, okay? So long story short, we always have to consider bending moment. So bending moment M equal to force multiplied by eccentricity need to be considered. Okay, need to be considered. Okay, so if this is the case, let's do another drawing here, right, to show the fat eccentricity, right? So I have a column as I shown before. Now before I just have a compression force. Now supposedly this is the center line of the column. I'm only showing the top part of it, okay? And now I have a force not exerting in the center, but force exerting here with an eccentricity of E. Okay, so from the mechanics materials, we know that this is equivalent to a section. This is equivalent to a section with a force right here and, and a moment right here. Okay, and the distance E is the eccentricity. Distance E is eccentricity. Okay, so let's take a look. When I have a bending moment going this way, and I have a force right here in the center, right? So I have actually a stress distribution, right? Is that stress distribution, right? So I'm going to draw the stress distribution caused by this action here in red. And now this side would see tension, and the other side supposedly will see compression. and then we're connecting them through here. All right, so this is tension, and this is compression. Okay, now we said this before, steel is good for tension and concrete is good for compression, right? So now we actually have this, but this is only caused by the bending stress. This is only caused by the bending moment, is that right? We also have to consider the compression. Sorry, let me use black. Get this thing fixed here. And then use a blue color to get it fixed here. All right. We also have to consider the compressive stress, right? Because I have a uniform stress generated by the P, right? By the compression force. Okay. So black color from P and red color from moment, right? So that is what we're seeing here, right? So the actual stress, right? Finally, the actual stress should look like something, look like something like this. Use it up. It'll look like something like this. Okay. And now, if it looks like this, right? We are trying to say here is that we always have more compression. We always have more compression than tension. We always have more compression than tension. Is that right? Always have more compression than tension, right? So in the column, okay, in the column, it's very hard, very unlikely to see tension failure in column, okay? So I'm just gonna put it here. Very unlikely to see tension failure, tensile failure. More likely to have compressive failure. Now, what does it mean? It means that usually the column fails when the compressive stress reaches the FCU. FCU. This is the compressive strength of the concrete. Compressive strength of the concrete. Okay. Okay. Now, from mechanics materials, let's do the stress distribution. Right? So that is to say, if follow the mechanics materials, P over A, which is the compressive stress, plus the bending caused the compressive stress, and Y over Fi, when that equal to FCU, it fails. It fails, right? Then I want to divide FCU on both ends, so I have P over FCU multiplied by A plus My divided by, let me clean this up, My divided by I FCU I equal to 1. Equal to 1. Okay. Now you have seen this equation before from mechanics materials. Okay. But to design concrete, let's define some terms. So define let, okay, at Cu multiplied by A to be P max. That means that's the maximum compression. That's the maximum compression a column can take. And let FCU multiplied by I divided by Y equal to maximum bending moment. Maximum bending moment. Okay, and you can pre-compute this. So with this two, I can further convert my equation to become P divided by P max plus M divided by Mx. And this equal to 1. This equal to 1. All right. And this equation right here, is called interactive equation, interaction equation. This is called interaction degree. Okay. What does it mean? It means that I will plug my applied axial forces and applied moment to this equation. And whenever they reach 1, it means it fails. It means the concrete column fails. Concrete column fails. Right? So what does it look like in the or on the curve, on the chart, right? So I'm going to draw the chart. I'm going to say, okay, let's show the diagram, right? Show the diagram. So show equation 1 in diagram. Right? What does it look like? So let me use the right space here, okay? So I'm going to draw an axis. I say this is m divided by m. And vertical axis, so this is p divided by p max. Okay? So when I have here, let me use red point. This point here, I say this is m divided by m max equal to 0, p divided by p max equal to 1. All right, and I have this point right here on the horizontal axis when m divided by m max equal to 1, p divided by p max equal to 0. Right? Then the failure line will look like this. The failure line will look like this. And this is for the compression side of it. This is for the compression side of it. Okay. Now, if assume materials behave linearly elastic. Linearly elastic. What does it mean, right? What does it mean? It means if I draw the stress strain curve of the materials and they follow a straight line, and it failed here in terms of compression FCU and failed here in terms of tension FT. And then let FT equal to FCU in terms of absolute value. Okay. If that's the case, if the material is elastic, right, I can also have the other 2 points. And this point is essentially here is -1 when m divided by mx equal to -1, then p divided by p max equal to 0. And at the bottom here, I have m divided by mx equal to 0, p divided by p max equal to -1. Okay, then I connect all these points. Connect all these points. All right, I have a diamond, right? I have a diamond. All right. So inside this region, okay, I'm gonna do a shaded area. Okay, inside this region, equation 1 is smaller or equal than 1. Right? So the dots inside this region means the equation is smaller or equal than 1. Outside, I'm gonna use blue here, equation is bigger than 1. Okay, so inside is safe, outside is failure. Okay, so this is the concept of interaction diagram. Okay, essentially we're going to say that assume we know the material is linearly elastic, and we assume that we can find these lines, these curves, right? And given applied moment and force, axial force for a particular column, for this column with the size and dimensions and rebars are known, you can find out if this point, this point, this blue is bad. you can find out in this point whether it's safe or it's failure. Okay, and that's how you design our column. That's how you design our column. Okay, but this is so nice, right? This is so nice, right? However, in the reality, concrete and well, concrete in this case, the concrete does not behave linearly elastic. All right, so need to redraw interaction diagram. Okay, which means actually interaction diagram for concrete is nonlinear. It's not nice straight lines of this. It's not nice straight lines like this. Okay, so this is very important to know. This is very important to know. All right, since it is not so straight line like this, what is supposed to look like? What is supposed to look like, right? So to understand that, okay, to understand that, let's do this. Let's say interaction diagram. Okay, and then let's do stress analysis first. Let's do stress analysis first. Okay, so for a given column, first of all, for a given column, okay, loaded with P n and M n equal to P n E. Okay, what do you actually see? What do you actually see? So I have a column. And this is the center line of the column. And say I have a loading, red here, and with a eccentricity, with an eccentricity of E. Okay, and I have a size, a dimension of this column right here. Let's just say this has a dimension of H. Okay, H, and I'm going to do a cross-section cut. And what we're looking at, right? What we're looking at is actually, so let me draw this way. Maybe it's better. I'm gonna flip the section, right? I'm gonna flip the section. Be careful. See that when my force applied to the column, this direction is H, okay? This direction is H. So I have my section right here. This is H. I have my compressive reinforcement on the top. I have a spacing of a D prime. And I have the width of the beam, V. And I have the bottom of the rebar here. Now the depth of it is D. So this is my cross section. Okay, this is my cross section. So we know bending very well, right? We know bending very well, right? So we can see the stress distribution, but be careful now. Be careful now. This stress is combined stress. So also look at the strain. The strain is also combined, right? So the strain distribution will look like something like this. You see more of compressive zone. You see more compressive zone C. And it doesn't really matter is it combined or just purely bending. It will fail when the concrete reaches compressive strain epsilon Cu. And my bars on the top will see a compressive strain epsilon S prime. And then I have the bottom bar here to see a tensile strain of epsilon S prime. You notice that the bar is not yielded. The bar is not yielded. We don't know that for sure, right? We don't know whether the bar will be yielded or not. We don't know the bar will be yielded or not. Okay? All right. So if this is a strain, diagram, right, we will proceed to draw the stress diagram. So the stress diagram looks like this. So this is the compressive zone, but you know what? We're gonna do the equivalent stress, right? Equivalent stress. So the actual compressive zone looks like this. Okay, so this equivalent compressive zone look like this. And this is A equal to beta 1 C, remember? And then this value here is 0.85 F prime C. Okay, and I also have a compressive stress from the steel, Fs prime, and then tensile stress from the steel, Fs. Okay, all right. And then to summarize the total forces, right? So this is strain, this is stress, right? To summarize the total forces, right? Total forces. I now have a compression from the steel, which is Cs, equal to As F prime, As prime, Fs prime, and the area, right, minus a As prime and 0.85 F prime C. Remember, this is from the W reinforced calculation. I have concrete compression CC equal to 0.85 F prime C AB, and I have my tension T as equal to As Fs. So this is internal forces. Okay, internal forces. Now, one thing I haven't drawn is the resultant forces. That is, or you can call it external forces. External forces. So the external forces just looks like a Pn, and then Mn, which is equal to Pn multiplied by E. Okay. All right. So now, this essentially acts as the set of the equation, right? The equilibrium is that we need to set internal forces to be equal to resultant forces. Okay, that means Pn. I'm going to use blue here to differentiate. So Pn, well, left or right, right? So the internal forces here in this case is the Cc plus Cs, the compression, right? The compression, right? Right, the compression, and that has to equal to the total compression forces. So here on the right hand side, this is Pn. Here's the right hand side, it's Pn. Okay, so Pn in this case will equal to 0.85 F prime C AB plus a As prime bracket outside F prime S minus 0.85 F prime C equal to Pn. Equal to Pn. Okay, and also we need to require the bending moment. Okay, bending moment in this case equal to 0.85 F prime C AB multiplied by the distance, which is half h minus half a. You've seen this before from W reinforced section. And this is As prime bracket inside Fs prime minus 0.85 F prime C, then multiplied by a distance, which is half h minus d prime. Okay, and don't forget the tension. Don't forget the tension caused the moment. Okay, that is As Fs d minus half h. D minus half h. You see that we're summing the moment, okay? Just to put a note here in case you were wondering. This is summing the moment with respect to center of the section. The half h thing, okay? The half h thing. Okay, so we're basically summing the moment right here, the half h line, half H line. And the right side, this equal to Mn or Pn multiplied by E. Okay, Pn multiplied by E. All right. So now supposedly given the section, by adjusting A, you can get different Pn and Mn to form this interaction diagram. Okay. All right. Now let's continue our discussion tomorrow on how to draw the interaction diagram where we have more time, and I want to save it because now we're going to get into the details. Okay. But this is the concept of the column for interaction diagram. All right. So I'm just going to stop here. If you have any question, please shout out right now or send me the messages. Okay. Any question regarding this? You getting this whole notes here? Any questions?
I have a question about that last equation there for the moment.
Yeah.
Is that last little bit, the plus ASFS D minus H over 2, that's included in that equation, right?
Yes. So this whole thing on the left.
Okay, cool.
Okay.
I looked down and then I looked back up and then it was there and I wasn't sure where it came from.
All right. Let me rewrite it for like one line here for you, okay? So you can see it better. Half H minus D prime plus AS. It's pretty long, that's why I have to do 2 lines. But this is essentially what it is.
Awesome, thank you.
Yeah, sure. Anything else? Any other questions? Now, column is the most important thing, if not in the whole design process. We talk about the beam, we have the flexure, we have the shear, and this column bending diagram, interaction diagram is very important for structural design. So if you have any question about the concept, now is a good time to ask these questions, okay? Any questions? Now clear about this concept, the compression, the bending. Okay, now be careful when I draw this right here, this is assuming the material is linearly elastic. Okay, you see that for the next lecture, this diamond shape diagram is not true, all right? Because the material is not true, because the material is not linearly elastic. The material is not linearly elastic. Okay, all right. Anything else? Any other questions? Any other questions? Anything else? Okay. If you don't have any other questions, let's meet again tomorrow, Thursday. We'll go over the exam quickly, and also we'll continue to talk about interaction diagram, finish the column design part. Okay? All right, well, thank you very much.
Do you know when we'll get our exam scores back?
Yeah, I mentioned it twice in the beginning of the lectures.
Sorry, I joined late.
Oh, okay. I was grading, I already like quarter way through. It will be finished either late tonight or tomorrow morning, definitely before tomorrow lectures. And then we can talk about tomorrow lectures.
Okay, thank
you. You will see the grading online. I'm doing the grading right now offline, but I will upload them through the speed grader and also Canvas as well. So you should see the grade. You should be able to see the grade tomorrow morning, the latest. Okay.
Good. Thanks.
Yeah, no problem. Anything else? This is very important concept. Okay, the column design. I really hope we have more questions from it. But you know, if you don't, that's fine. We can meet tomorrow again, where we have more time for questions. Okay. All right. Okay. Anything else? Burning things, let's get them out right now. We have a few more minutes left. Anything else? Okay, okay. If there's nothing else, we can talk about the column and exam tomorrow, okay? Thank you very much. I'll see you guys tomorrow, 2 o'clock. All right? Appreciate it. Okay.